Hi, we're going to look at this Leetcode problem. I have been watching several YouTube videos about it, but I still find they are missing a very important explanation. So the problem is like this. They gave us a sorted array in ascending order, and we need to return k closest integers to the target x. For example, if we have 1, 2, 3, 4 here, 3, 4, 5 here, and we want to return four closest integers that is closest to the target 3, which is 1, 2, 3, 4. And also we have a tie break here. If the distance of two integers are equal to the target, then we return the um, the smaller one as our result. So what we're going to return right now is just a sorted array, which is also a sorted array. It's just like the part of the original array. Um, on the internet, the most efficient solution should be like this. Should use a binary search. What we're searching here is actually very important. This is the first step of understanding this. What we're searching here is the left index, leftmost index of the result window. Remember, the result window is just parts of the array. For example, this is my uh, original array. My result window may be this, and this is we're searching the leftmost index here. So in this algorithm, the first important part will be like the possible range, the initial search range for the leftmost index should starting from the start of the array and the length of the array minus k. Because if the leftmost index is here, then we don't have the k elements to return for, so we don't have the windows there. So the largest possible value that L can take is length minus k. So that's the first. That's why we have the initial search range for the binary search. Um, the rest of it is pretty mundane. I have this. This is just calculating the middle index, and also you can see that the most confusing part would be this condition. I have watched several YouTube video about it. I don't think they have done a really good job on explaining the examples, on explaining how to code, why this works, but they just kind of are a little bit ambiguous on explaining this condition. That's what this video is about. So I have layout the laid out uh, the conditions here, and I have three cases here. So the middle is the pivot of the binary search, okay? And in case one, obviously, what we want to do, we want to update R equals to the middle, update the end index equals to the end index equals to middle. Uh, because in this case, we notice that this guy is obviously closer than this guy, right? So the start index uh, is someone in this part of the area. So what we need to do is we need to discard all the possible ranges here because they are apparently very much far further than the middle index. In this case, what we're gonna do is just updating it. So let's just check the condition a little bit. X minus the middle would be something negative. However, the middle plus k minus x would be something positive. In this case, so the condition will have distance 1 is smaller than distance 2, right? And then the result would be updating the end index to be the middle. Let's first check out case 3 here. So for case 3, it's actually very similar. Now we're going to see here, this the middle, like the end index would be someone here, some area here. And you can see what we want to do is trying to update the left to be this guy, because that will make our possible range closer than x. So we're going to update, it's going to be middle plus 1. Why do we have a plus 1 here? Because we already know that we already know that we can move a little bit further towards x by plusing 1. Let's check out our conditions here. So when x minus the middle, that would be something positive. When the middle plus k minus x would be something negative. So we have distance 1 is bigger than distance 2. And what we're gonna do, we're gonna update left. Oh, we're gonna update, sorry, start index to be middle plus 1. And then we're going to look at case 2. Case 2 is a little bit tricky here. So we first notice that both distance 1 and distance 2 are positive. So what we are comparing here is actually the distance, the geometric distance, the absolute value of this segment. So if this is D1, this is D2, if D1 is less than D2, so if D1 is less than D2, obviously we know that, okay, we need to include this element here. So what are we gonna do? We're gonna update our start index by including it. If distance 1 is bigger than D2, oh sorry, I made a mistake here. So if distance 1 is smaller than D2, which means this element is closer than middle plus k here. So what I wanted to include is actually the middle element here. So we're going to update the end index, because the end index is the upper bound is for the possible range for the leftmost index, right? And when the distance 1 is bigger than distance 2, and then we're going to include the middle plus k element here. So we're going to update start index to be leftmost plus 1. And when the distance 2 and distance 1 is equal, now we have to use the tiebreaker here, which means we have to include the middle, which we're going to do the same by using an index, updating an index to be the middle. Now we can say that every time when the distance 1 is less than distance 2, we have to update our equal, we have to update our end index. Every time when distance 1 is bigger than distance 2, we have to update our start index. So that's why the condition works.